Okay, now we'll see that work done for various non-flow processes. Okay, work done for various non-flow processes means there are various processes like constant volume process, constant pressure process, adiabatic process, polytropic process. So for different processes there will be different work output and different things will be there. So we'll discuss each and every process. Okay, so first of all we'll discuss about constant volume process. What is going to be a constant volume process? So if we consider the ideal gas equation for that system, then this system will give us PV equals to MRT. Now in this equation volume is going to be constant, volume is going to be constant, and in that mass is also going to be constant, R is also going to be constant. That is characteristic gas constant is going to be constant, R constant, and temperature is variable. So if volume is constant, we can easily write pressure is proportional to temperature. So from this we can write P1 by T1, P2 by T2. Okay, these two will be equal, and these two will be known as ideal gas equation for constant volume process. That means you need to remember for constant volume process, P1 by T1 is equals to P2 by T2 always. Okay, this thing will be very useful for solving the questions later on, solving the questions of cycles, power cycles like Brayton cycle, Otto cycle, diesel cycle. This thing will be very important, so you remember this. So again we can see that volume is constant. Since volume is constant, then dV, derivation of constant, is always 0. So dV is always going to be 0. And what do we know from work done? Work done is integration of P into dV. Since dV is 0 and work done is going to be 0, that means what? PdV work for closed a constant volume process is always going to be 0. Okay, so we know. So another thing we have said that for a closed system, if we project the graph, project the plot in volume axis, then we can get the work interaction. Okay, now these are the two, these are constant volume. For a constant volume, okay, this will be heat addition. That's why pressure will be increasing from 1 to 2. Okay, pressure will be increasing but volume is constant, and this is going to be isochoric, that means constant volume heat rejection. Because there is heat rejection, the pressure will come down from 3 to 4. These are the two processes. Okay, now we have proved here that work done for a constant volume process is 0. Okay, now if we come out here, what will be there? Then if we plot, what we have said that if we project the plot in volume axis, then this area will give us the total work output. Now if we plot this in volume axis, this will only be a straight line. This will be also be a straight line. So for a straight line, the area is going to be 0. Okay, area is going to be 0. Only length would be there, breadth would be no there. Okay, so that means if we project the plot in volume axis, the area is going to give us 0. That means the total work done in constant volume process, PdV work, is going to be 0, which we have proved here. Now we'll see about constant pressure process. Okay, so for constant pressure process, ideal gas equation is going to be again same, PV equals to MRT. Now in place of V, P is going to be constant. P is going to be constant, M and R are constant, and T is going to be variable. So from this equation, if these things are constant, we can say that volume is proportional to temperature. So in place of that, we can write that V1 by T1 equals to V2 by T2. This thing will be for constant pressure process, V1 by T1 and V2 by T2 are equal. So this is going to be known as ideal gas equation for constant volume process. Again, this is very important. We need to remember this for solving other questions. So this is very important. So from here, what we know that pressure is going to be constant. So from this integration, from where we can derive the W, that means integration 1 to 2. 1 to 2 means from state 1 to state 2. From state 1 to state 2, pressure is going to be constant, and we need to derive dV. Okay, so if pressure is constant, that means pressure would come out of the integration. Here pressure is coming out of the integration, and integration of dV is going to be V only. V from 1 to 2. That means we can directly subtract volume at state 2 minus volume at state 1. So this thing is going to give us the work output for a constant pressure system. Now if we see it graphically, there are two processes I have drawn from 1 to 2. 1 to 2 means here the value of pressure would be constant, here the value of pressure would be constant. So constantly, with a constant pressure, it is going from volume 1 to volume 2. Okay, it is keeping the pressure constant, it is going from pressure 1 to pressure 2. So this process is known as constant pressure expansion process, and this process is known as constant pressure compression process. Okay, pressure is same, volume is increasing in this process, volume is decreasing in this process. Okay, so and we have said earlier, if we plot the project, or if we project the area in volume axis of that plot, this will give us the work done. Okay, so let us take this one, 1 to 2 is 1 to 2. Okay, this is going to be isobaric expansion. So if we project this one, then what is going to be the area? This area is going to be this pressure into this distance. This distance means volume V2 minus V1. Okay, so from here this area is going to be pressure, that means this into this. This means this means pressure. Okay, pressure into this distance. This distance means what? V2 minus V1. Okay, this will give us the work exactly same as this one. Okay, so this is the work done expression for constant pressure process. So this thing and this thing we need to remember for solving questions. Now we'll discuss constant temperature process. Now what is going to constant temperature process? That means from state 1 to state 2, whatever process is there, through the whole path the temperature is going to be constant. Now if you write the ideal gas equation for this constant temperature process, this will be PV equals to MRT. Now here M is constant, R is constant, T is also constant. So from here, if all these three are constant, you can write that PV is also going to be constant. Okay, so if PV is constant, that means what? Pressure at any path, any position of this path is going to be constant. So we are taking both the final states to 1 and 2. So we can write that the product of pressure into volume is going at state 1 is going to be equal to product of pressure into volume at state 2. Okay, so these two are going to be same. Now if we need to derive the work output from this, we know that work done is equals to pressure into P into dV, integration from state 1 to state 2. Okay, now this pressure can be written from this equation, this pressure can be written as constant by V. From here we can easily write that pressure is constant by V. Now if you replace this P here, in place of this P we can write C by V. That means C by V into dV. Now since C is constant, so C will come out of the integration. It will come out of the integration. Now we need to derive, now we need to integrate dV by V from state 1 to state 2. Okay. Now since this is constant means what? Product of pressure into volume. Now at any state this is going to be constant. So we can take either at state 1 pressure 1 into volume 1, or at P2 into V2 at state 2. Okay, we can write anything in place of C. At any place we can take pressure into volume. So I am writing P1 into V1. You can also write P2 into V2, is your wish. Okay, so here I am writing P1 V1, that is the value of constant. Now if we integrate this dV by V, this is going to give us natural log of V. From state 1 to state 2, it is going to be V2 by V1. Rather remembering it like P1 V1 into ln V2 by V1, we must remember it by final volume by initial volume. Otherwise there could be a process like this 3 to 4. So for 3 to 4 there is no 1 and 2, but we will remember, if we remember this by 1 and 2, we will only search for state 1 and state 2. Either it may be constant temperature or not. So better we remember it by final volume by initial volume. Okay, so constant into natural log of final volume by initial volume. Now if we write this again here, now from this equation we can easily write V2 by V1. V2 by V1 is going to be equal to P1 by P2. Okay, so this same equation can be written as P1 V1 into ln P1 by P2, initial pressure by final pressure, but here final volume by initial volume. And you can also replace P1 V1 by P2 V2. These two will be same thing only. So it's your wish what you are going to write, but this final volume by initial volume can be replaced by initial volume by initial pressure by final pressure. Okay, so in this way we can find the work for constant temperature process. Now if we plot this graph here, this is going to give us a curve like this from state 1 to state 2. Now why this curve is going to be like this we will discuss later, but for now we can remember that for constant temperature process this is going to be the plot which we need in constant temperature process. And area under this curve, if you project the area under this curve in constant in volume axis, then this thing will be known as the work output, or whatever the work we are interacting. By projecting this area in volume axis, we can easily find out. Okay, the next thing is going to be adiabatic process. So for adiabatic process, this is the ideal gas equation. Okay, PV to the power gamma is equals to constant. Gamma means a ratio of specific heat at constant pressure to specific heat at constant volume. That means gamma will be equals to Cp by Cv. Okay, this will be gamma. So PV to the power gamma is equals to constant. That means at any state P1, suppose at state 1, the product of pressure and V to the power gamma is going to be same as the product of pressure at state 2 into volume to the power gamma at state 2. Okay, this indicate this one. Okay, so from here we can write pressure is equals to C by V to the power gamma. Okay, from here. Now if we need to derive the work out from here, it is integration from 1 to 2 P into dV. Okay, now in place of P we can replace it by C by V to the power gamma into dV. Now C is constant. C is constant means C will come out of the integration, and we need to integrate this dV by V to the power gamma. So if you integrate this, this is going to be like this. Okay, V to the power minus gamma plus 1 by minus gamma plus 1. Okay, so from 1 to 2. Now we have put it here like volume 2 and volume 1. Okay, in this place what happened, we have taken a minus common from numerator and denominator. We have taken a minus common and cancelled it out. That means V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma, here becomes V1 minus V2. Same thing, and 1 minus gamma becomes gamma minus 1. We have just taken the negative sign common and we have cancelled out. Okay, so from here we have directly multiplied this with these two terms. Okay, these two terms we have directly multiplied. Now V1 to the power 1 minus gamma, we can write it like this, V1 by V1 to the power gamma. We can easily write it like this, simply indices. Okay, the simple indices formula gives us, we can write it like this. Okay, now from here this part and this part will be getting cancelled. V1 to the power gamma and V1 to the power gamma will be cancelled, so remaining will be P1 V1. Now here what happened, P1 V1 to the power gamma, we can replace it by P2 V2 to the power gamma. From here we can replace P1 V1 to the power gamma with P2 V2 to the power gamma. We are replacing this so that we can cancel out V2 to the power gamma and V2 to the power gamma. Okay, so for cancelling these two, we are replacing these two. P1 V1 to the power gamma, we are replacing by P2 V2 to the power gamma. Now these two gets cancelled. Okay, so what is remaining from here? P2 into V2 and P1 into V1 from here. So the final expression for work done comes like P1 V1 minus P2 V2 divided by gamma minus 1. That is P1 V1 minus P2 V2 by gamma minus 1. This is the work done equation, work done expression for our adiabatic process. Okay, this would be the work done equation. And if we plot them in PV diagram, the graphs will be like this. A slope would be slightly higher than the isothermal processes. Okay, slightly higher than the isothermal processes. And again, if we project the area of these plots in volume axis, this area will give us the work interaction. Okay, and we can easily find it using this expression. Okay, this is adiabatic process. Okay, the next thing would be polytropic process. The polytropic process would be exactly same as that of adiabatic process. The only difference would be that in place of gamma there would be N. Their gamma was adiabatic index, which was the ratio of specific heat at constant pressure to specific heat at constant volume. But here it would be N, which is known as polytropic index. Okay, everything will be same. Everything, every derivation, each and every point would be same. Only thing is that in place of gamma there would be N. In adiabatic process, N value, you can take N value as the value of gamma. And what is N value? N value will be always less than that of gamma and greater than that of 1. It will be between 1 and gamma. Okay, remaining that part, everything would be same. Only the graphs would be slightly having the graphs would be having only just a greater slope than adiabatic index. Remaining everything would be same. Even the graphical representation would be same, but the slope will be just in a lower side. Okay, remaining every process, even the work work expression which was there P1 V1 by P2 V2. In adiabatic process it was gamma minus 1 in the denominator. Here it is n minus 1. N is polytropic index. Remaining everything would be same. Okay, we can say that every closed system equation can be written as PV to the power k equals to gamma. So in this board we need to find k value for each and every process, isothermal, isobaric, isocoric, adiabatic, polytropic. For every process we need to find the value of k. Now what is the significance of finding this value k? Why do we need to find this k? Because if you remember in the last board we have discussed some of the important processes in closed systems such as isobaric, isocoric, every process, whichever the processes are listed here, every processes was discussed. But in these processes, some of the processes like isocoric or isobaric, we knew how the graph would be. That means in isobaric the graph line would be horizontal in PV diagram. In isocoric the lines would be vertical, the graphs would be vertical in PV diagram. But there are some of the processes which we have discussed like isothermal, adiabatic, polytropic. For this what we have done, we have drawn some curved lines on the PV diagram. We do not know how it is going to look with respect to each other. That means suppose there are two processes, isothermal and adiabatic and polytropic. Three processes are there. Now if we plot them in PV diagram, how are they going to look with respect to each other? Which is going to be more curved with respect to each other? Okay, so to know the behavior of these curves, we need to find the value of k so that we can plot it in a PV diagram. Okay, and we know how this plot is going to look when we plot it in a certain process which contains all the three processes like isothermal, adiabatic, polytropic. If we plot all of them together in a PV diagram, how are they going to look? Okay, so first of all, to find the value of k for isothermal, PV equals to constant. Okay, that means here k is going to be 1. Okay, if k value is 1, then PV is going to be constant. So for isothermal process, we can say that k have this in this thing k is equals to 1. Okay, isobaric process here pressure is constant. So for volume to be 1, k must be 0. Okay, so isobaric process k is equals to 0. Then only this equation can convert into pressure equals to constant. In isocoric, what happens in isocoric, volume is constant. Now to say volume is constant, we can convert this equation in like this. Okay, V equals to C by P to the power 1 by K. Now if you put K equals to infinity, then only this is going to give us a constant value. Here it is a 1. It is not like that always it is going to give 1, but we can say that it is going to give a constant value. V is going to be constant. Okay, so for volume to be constant, K must be infinity. Okay, now for adiabatic process, PV to the power gamma is constant. Now for turning this equation to this equation, K must be equals to adiabatic index. Okay, that is gamma. Gamma means ratio of specific heat at constant pressure and specific heat at constant volume. The ratio is going to give us gamma. So here K is gamma. For polytropic process, in the same way, K is going to be N. Okay, now we can plot these things in PV diagram and we can find out how these things are going to look in a PV diagram. All the processes are going to look in PV diagram. Okay, now we are going to plot the different processes in this diagram. So if we plot this diagram, we can always say that this is going to be isocoric, that means constant volume process in PV diagram. Okay, so we can say that this is volume equals to constant. And for constant volume, what was the value of K? The value of K was infinity. Okay, similarly in this way also we can write V is equals to constant and K is equals to infinity. And we all know that this line is going to represent the isobaric process. Isobaric process means constant pressure process in PV diagram. Okay, so we can write here that pressure is equals to constant. And for constant pressure, what was the value of K? The value of K was 0. Okay, the value of K was 0. Similarly, we can write it here, pressure is equals to constant, K is equals to 0. Now, we can see that clearly from here to here, K is increasing. That means here K is equals to 0. Now, if you draw some lines from this place, we can see that K is slightly increasing up to infinity. when it is converting from constant pressure to constant volume, K is increasing from 0 to infinity. So we can say that K is increasing in this way. Now there are three curve lines which you have drawn. One is for isothermal, one is adiabatic, and one is polytropic process. Okay, so let us draw three lines. Okay, now for polytropic process, what we have said that the polytropic index, what is going to be the polytropic index? We have said that, if you remember, we have discussed it in last video, that for polytropic process n is going to have the value of between 1 to gamma. That means n should be greater than 1 and gamma should be less than gamma. Okay, that means what? 1 is going to be the smallest, then there will come the polytropic, then there will come the gamma. Okay, gamma value for air is 1.4 and 1 is 1, n is something that will be provided in the question. Okay, it will depend upon the polytropic process. So for three processes, there are three processes isothermal. So as K is increasing in this way, that means smallest one must be here. Out of these three, 1, n and gamma, smallest one must be here, because this is increasing in this way. So slightly bigger will be here and slightly bigger will be here. So you can say that K is equals to 1 will be here, K is equals to n will be here, K is equals to gamma will be here. Okay, because if it is increasing in this way, the smallest one will be here, 1 will be here, n will be here, and gamma will be here. Okay, so if you remember, for which process K was equals to 1? K was equals to 1 for isothermal process. For which process K was equals to n? K was equals to n for polytropic process. For which process K was equals to gamma? It was equal to gamma for adiabatic process. Okay, so you can easily say that this is isothermal, this is polytropic, and this is adiabatic. Okay, now if you draw these three processes, isothermal, polytropic, adiabatic, in a PV diagram, or suppose there is a cycle consisting of all these three types of processes consisting of a cycle, and you need to draw it in PV diagram, you need to remember that isothermal will be slightly flatter, as in a slightly increasing manner it would be polytropic, and slightly in a vertical side it would be adiabatic. So these are the plots you need to remember while constructing a PV diagram with this type of process, isothermal, polytropic, and adiabatic. Similarly, in this side of the board, we can say that here K is equals to 0, K is equals to infinity. So K is increasing in this way. So again, if we draw three of the processes, isothermal, polytropic, and adiabatic, this will be obviously K equals to 1, this will be K equals to n, and this is K equals to gamma. Okay, there also isothermal is slightly flatter, adiabatic is in a slightly vertical side, and polytropic is in the middle. Okay, so the purpose of this whole thing is to remember how you should draw these type of processes, polytropic, adiabatic, and isothermal processes in PV diagram, remembering their slopes. Okay, these are the types of slope which we can get by determining the value of K, which we have done in the last book. Okay, so now we'll see slope for different closed system processes. Okay, these are some of the processes, constant pressure, constant volume, all these processes are there. We need to find the slope for each of the plots in PV diagram. Okay, so this is the PV diagram, and this first one is constant pressure process. So for constant pressure process, slope, we know that slope is equals to tan theta. Here theta is equals to 0, because this is completely horizontal. The theta it is going to make with the x-axis or the volume axis is going to be 0 degree. So the slope is going to be tan 0 equals to 0. The complete opposite would be here, that is constant volume. It is vertical line, vertical to the volume axis. Vertical to the volume axis means the angle it is going to make with the volume axis is 90 degree. And again slope is equals to tan theta. Tan theta is equals to tan 90 degree. Now tan 90 degree is infinity. Okay, that means the slope for constant volume process is infinity. The next processes will be in the next board. Okay, the next process will be constant temperature process or isothermal process. That is, the temperature is going to be constant throughout the process. Okay, Now while we are finding the slopes for constant pressure and constant volume, we already knew that these are horizontal and one is vertical. Okay, so the angles are already known with respect to the volume axis. One is 0 degree and one is 90 degree. Okay, these things we already knew, but this is a curved line. In isothermal process, this is a curved line. How can we measure the angle? If you take different points, in different points the tangents are going to be different. So each of the point the tangents are going to give the measure of angle differently. Okay, so in a particular manner we cannot find the slope in isothermal process. Okay, the slope in isothermal process is not going to be constant. So what happens is, as you have seen in your different classes, how for a curve how do we take the slopes in your 11th or 12th standard 12 physics, when you were doing some practicals, there you had to draw the slopes. So how did you do? We take a small tangent, we take the sides in one in vertical direction, one in horizontal direction. Okay, after that if we take the ratio of this, then they used to give us the slope. Okay, what is the main concept between these is, if we take a small tangent and if we draw these lines horizontal and vertical, then this horizontal line and this tangent is going to make an angle theta, suppose. Now what is going to be, according to the triangle law, what is going to be the tangent of that theta? That means tan theta. Tan theta will give us this distance by this distance. Okay, this distance is, as it is along the p axis, that means this distance we will take dp, and this small distance we will take dv, because it is in the along the volume axis. So from this small triangle, tan theta is going to be dp by dv. So to generalize this, we have taken arbitrarily one point somewhere in between the slope, that means in this curve we have taken a point arbitrarily, and we have taken a small tangent and we have drawn this line to generalize the expression of slope, that is dp by dv. This is nothing, we are taking it in a general case. After that, if someone asks me to find this in this point, then they will easily give me some values of pressure and volume at this point, so we can easily put it in the final expression and we can find the slope. So to generalize this, we are doing it in this way without knowing the theta. Okay, so to find out the slope, what you can do, the only thing we know for the constant temperature process is that PV equals to constant. Okay, now these are the terms with d in them, that means with derivation terms in them, we need to find out the slope. So to get the derivation term, if we derivate this in both sides, okay, what you will see that derivative of p into v is going to be 0, because this is constant. For constant value, derivation is 0. So this is again the chain rule or derivation of uv. So derivation of uv is 1 is going to come out, and the derivation of other plus that thing will going to come out, and the other thing which had come out in the earlier phase multiplied by derivation of this. This will give us the expression for derivation for uv terms. That means one variable multiplied to another variable. So from this equation we can find that dp by dv, which is going to be the tangent of the small slope. In general case will give us dp by dv equals to minus p by v. So this is in generally the slope for an isothermal process. For each point there will be a pressure term, pressure value and volume value. By putting it in, suppose in this point they have given some pressure value and volume value. Now if you put this pressure value and volume value in this equation, you can get the slope in this point. Likewise we can find the slope. Okay, the next thing would be adiabatic process. Though it is adiabatic process, a different kind of process, but still it is a carbon PV diagram. So the procedure of finding that slope will be exactly same as that of isothermal. Procedure is same. I am not saying that slope is same. Procedure of finding this is same. Okay. So for finding the slope in adiabatic, the only equation we know for adiabatic is PV to the power gamma is equals to constant. Now again, to find the term with derivation or d term, we need to derivate this with respect to something in both the sides. Okay, so if you derivate this, the constant is going to be 0. Okay, now again this same uv rule you need to take, p is going to come out, then derivation of this one, then this one is going to come out, derivation of this. again the same UV rule you need to apply. Then after that we need to simplify in this way. Okay, now this is that, if we simplify this, it is going to be like this. Okay, so after that we need to find the ratio of dp by dv from here. Okay, so this, after finding dp by dv from here, this is going to give us the expression like minus gamma into p to the power gamma minus 1 by pv to the power gamma minus 1 by pv to the power gamma. And this is again going to be simple indices. That means to find the final power in v, we need to subtract v to the power gamma minus 1 minus gamma. Okay, that means this is going to give us v to the power minus 1. Okay, so for v to the power minus 1, v will come in the denominator. Okay, and this minus will go with p and gamma will come in front. Okay, so this is the final expression for adiabatic slope. That means slope for adiabatic process. And in polytropic process, this is going to be exactly same as adiabatic process, just in place of gamma there will be n. Gamma value we know, that is 1.4 for air, but n value depends upon something which will be given in the question. According to the question, you need to find out the value of n or the polytropic process. Otherwise the remaining thing will be exactly same as what we have found out in the isothermal process. Okay, simple UV rule we need to apply. Then simplifying this, we need to get the ratio of dp by dv. Then after that, while further simplifying this, we are going to get this expression. This is the final expression of slope for adiabatic process, and this is for polytropic process. Okay, so we have discussed some of the important work done procedures or work done equations for all the processes like constant pressure, constant volume, isothermal, adiabatic, polytropic. For all the processes we have discussed some of the work done equation. That means how we are going to calculate work done for these particular processes. And if you remember, while deriving these equations, we have boxed down some of the important equations and told you that these are the processes for that particular, these are the ideal gas equation for that particular process. Suppose if we are deriving the equation for constant volume process, we have boxed down one thing and we have told that this is going to be the ideal gas equation for constant volume process. Okay, and we have also told that these things are going to be very important. These things are going to be very important while solving the numerical questions. And the work done equations and work done formula for individually each and every processes are going to be very important. Okay, so we are going to explain one numerical in this board, and by solving this question we are going to make you understand how to solve this type of questions. And before solving this question, make sure that you know the ideal gas equation for each and every particular process. That is, for constant volume process, what is going to be the ideal gas equation and work done. For constant pressure process, what is going to be the ideal gas equation and work done. Like this, for each and every process, the ideal gas equation and work done equation you know. Make that sure, okay, before starting this question. So while starting this question, the question that is given is ideal cycle undergoes as shown in the figure, find V2 and W net. By saying this, they have given us this diagram. So in this diagram there are three processes, 1 to 2, 2 to 3 and 3 to 1. Okay, so in these processes they have given us some of the data, like for process 1 and 2. By seeing process 1 and 2, you can easily see that this is horizontal, and by horizontal this means constant pressure process. So for constant pressure process, pressure at point 1 and pressure at point 2 is going to be same. For process 2 to 3, they have given that PV to the power 1 to 1.4 is going to be constant. Okay, that means 1.4 is the gamma. 1.4 is the gamma. That means PV to the power gamma is constant. That is, it is adiabatic. And 3 to 1, they have given that temperature is constant. That means this is pressure into volume is going to be constant. That means this is isothermal process. So from this we need to find the volume at V2 and the W net. That is total net work done by this cycle. Okay, these things we need to know. So how to solve these questions? So first of all, we need to see that the first thing they have told us to find that what is V2. So this is V2. So the state 2 is connected to process 1 to 2 and 2 to 3. There is no connection between the process 3 to 1 and the state 2. Okay, there is no connection. So we need to find the volume 2 by using only process 1 to 2 or 2 to 3. But the question is, in the process 1 to 2, it is constant pressure process. So if you remember, for constant pressure process, the ideal gas equation was volume 1 V1 by T1 equals to V2 by T2. Now, not a single trace of temperature is given in this whole question, so we cannot find it by using this equation. Okay, temperature T1 and T2 are unknown to us. Even the temperature T3 is also unknown to us. In the whole question, no trace of temperature is given, so we cannot find V2 at first position. Okay, in process 2 to 3 also, pressure, the volume is unknown here, pressure is only known here. In this thing, only pressure is known, volume is known. So we have got two unknowns, volume at 2 and volume at 3. So we also cannot solve this by using 2 to 3. So let us see what we can get from process 3 to 1. So for process 3 to 1, what is going to be there? And one thing, I have solved this question in my copy, so I will show you the procedure up to where you just need to put it in the calculator and you will get the final value. So I will not put it in the calculator, I have already calculated. I will just put the final value after showing you the process up to where you just put the value and get the final answer. Up to there I am going to explain, and after that, after seeing my copy, I will just directly put the values. You can just match. Okay, so for process 3 to 1, 3 to 1 is what? Isothermal. Isothermal means PV equals to constant. PV equals to constant means P1 V1 equals to P2 V2. Okay, so P1 V1 equals to P2 V2. But this isothermal process is consisting of state 1 and 3. So there is no process 2. So we need to rename this as P3 P1 V1 equals to P3 V3. Okay, because state 2 is not connected with isothermal process. Okay, so P1 we know from this state, P2 we know from this state, V1 we also know, but V2 we don't know. So from this whole V3 we do not know. So from this whole equation, only one thing is common, V3, which you can easily find out. So P1 value is given as 400 kilopascal, V1 value is given as 1 meter cube, P3 value is given as 100 kilopascal, and V3. So from this equation, you can say that V3 is going to be 4 meter cube. Okay, so now we can put this in this equation. That means if one of the unknown is solved, which we are trying to solve by considering process 2 to 3, which is adiabatic, we had two unknowns, volume at V2 and volume at V3. Okay, that means for adiabatic process, P1 V1 to the power gamma equals to P2 V2 to the power gamma. Okay, but here this process, there is no connection of state 1 with adiabatic process, so we need to change the name to P2 and P2. Okay, sorry, P3 and B3. So at first, before doing this step, there were two unknowns. Okay, volume at V3 and volume at V2. But after doing this step, up to this step, we have found out the V3. So in this whole part, only V2 is unknown. Okay, so by solving this, we can easily find out V2. Okay, so P3 by V3 by P2 the power 1 by gamma is going to give us the volume at state 2. Okay, now everything is known. P3 is known to you 100 kilopascal, P3 is known to you 4 meter, and P2 is known to you as 400 kilopascal. Okay, so now if you put in directly this into calculator, that is P3 is going to be 100, V3 is going to be 4 to the power 1.4 divided by P2 is 400 whole to the power 1 by gamma is going to give us V2. So from here V2 is going to be, if you put this in calculator, you will get V2 as 1.486 meter cube. 1.486 meter cube. So from the question, we have already found out the first thing which was asked to me. Okay, so V2 we have found out. Now we need to find the W net. W net, how we can find W net? We will find each of the W, each work done from each and every process. Suppose from process 1 to 2, there is going to be a W. from process 2 to 3 there is going to be another W, and process 3 to 1 there is going to be another W. So algebraic sum of all these three processes is going to give us the final work done, or W net. Okay, so for finding the work done from process 1 to 2, that means for W1 to 2, what is going to be W1 to 2? So W, if for constant pressure process, if you remember, the formula for W was pressure into V2 minus V1. Okay, and here we do not need to rename this because 1 to 2 is constant pressure only. So pressure for this constant pressure is given as 400. V2 we have found out V2 as 1.486 meter cube minus V1 is given as 1 meter cube. So we can easily find the process 1 to 2 as 194 kilojoule. 194 kilojoule. If you put this in calculator, you will get this. Okay. So for process 2 to 3, what is going to be the work done for process 2 to 3? 2 to 3 is going to be adiabatic process. Now if you remember, for adiabatic process, the work done equation was P1 V1 minus P2 V2 divided by gamma minus 1. But 1 is not there in adiabatic process. Adiabatic process is consisting of state 2 and 3. Okay, it is coming from 2 to 3. Okay, so we need to rename this 1 as P2 V2, and it is coming to 3. So the final stage will be 3. Okay, so from here P2 is known to you. P2 is 400. V2 is given as 1.486, which we have found out. P3 is given as 100 kilopascal. V3 is given as, V3 we have found out as 4 meter cube. Divided by gamma is 1.4 minus 1. So if you put this in the calculator, you can easily find that the work done which you are going to find from process 2 to 3 is going to be 486 kilojoule. Okay, we are going to find this as process 486 kilojoule. So for process 1 to 2 we have found out the work, for process 2 to 3 we have found out the work. Now we need to find for process 3 to 1. So process 3 to 1 is adiabatic process. Isothermal process. So for isothermal process, what is the expression for work done? The W3 to 1. So the expression for work done, which I have told you, that in place of constant there was either P1 V1 or P3 V3, whichever one you can take. So P1 V1, let us take P1 V1 into ln, and I have clearly told you to remember it by final volume by initial volume. So the final volume is 1 and initial volume is 3. Okay, so initial volume is V3. So V3 we have found out as 4, and the final volume is 1. So this is a compression work. So compression work is always going to be negative. And also, if you do not remember this, and if you directly calculate this, you can also find out that this is going to come as negative. So this is going to come as 554 kilojoule. Okay, 554 kilojoule. P1 V1, P1 is known, V1 is known. You can easily put, and you can easily get the value as minus 554 kilojoule. Now we need to find W net. What is going to be W net? W net is nothing but the algebraic sum of all the processes. That is W1 to 2 plus W2 to 3 plus W3 to 1. Okay, so from here, what was W1 to 2? W1 to 2 was 194. W2 to 486 kilojoule. W2 to 3 was 486 kilojoule, and W3 to 1 was minus 554 kilojoule. So if you add up all this, you will get the final answer as 126 kilojoule. So each and every processes is going to be important, and each and every work expression is going to be important for solving this type of questions. Now I hope you have understood how to solve these type of questions, and how we can approach if we see different types of processes in a cycle. Okay.